Hi, everybody. Thanks for being patient. We've got Kees here to give you a talk on gas well performance. Keep it super simple, which is good in life in general. I'll hand over to Kees and he can introduce himself. This will be our last webinar for the year because we've had to cancel our flow assurance one that we were doing in December due to unavailability of the instructor. But for the webinar, we'll try and keep you on mute. I'm having trouble muting everybody. So if you can just refrain from asking questions during the session by microphone. Happy to take questions on chat. And if I can, I'll answer them. But at the end of the session, we'll go over them with Kees to make sure I'm not telling you things that are incorrect because I'm not a production technology specialist. The rules for the webinar, questions using chat. If we don't address all the questions live, we'll follow up via email, but we should have time to answer all the questions. But you're always also welcome to send questions through by email at training@asandaengineering.com. We're recording the webinar and we'll put it on YouTube after the session if you want to revisit any of the aspects of the webinar. And as I said, feel free to ask further questions after the webinar by email if you want to. So without any further ado, I'll hand over to Kees to present. Okay.
Yeah, thanks, Anastasis. So good morning, good evening, good afternoon, etc. Yes, my pleasure to present. So I'm a production engineer, production technologist. I've worked for Shell in various countries for a long time, but I'm now sort of semi-retired and self-employed as a consultant and a trainer. This is a presentation I did a few months ago in The Hague for an SPE workshop. And it's basically about how to monitor gas well performance in as simple a manner as possible. Yeah, so I've worked in on gas wells for quite a while, like for the last 20-25 years, in all kinds of circumstances. So both prolific, large bore, offshore gas wells, as well as sort of the smaller, tighter onshore gas wells. We'll go through several topics. You know, first is a bit of an intro on why and how we're monitoring. Then we'll go into the equation part, trying to keep everything as simple as possible. And we'll use the well performance equations to also define an operating envelope where we can equip with alarms to be able to provide warnings if anything goes haywire. And I'll show how this monitoring methodology can give you like a record of well performance parameters, specifically inflow performance parameters, being reservoir pressure and inflow resistance. And I'll lift out two specific topics just to illustrate you know what you can do with the results. One is on condensate dropout and how it impacts gas well performance, and one is more on volumetrics. So it's all about deriving connected volumes and ultimate recovery from data. And we'll close off with some conclusion recommendations, and then you can ask questions. However, you can ask questions anytime during the presentation. Yeah, so don't hesitate. If there's anything unclear or you don't agree or you want to clarify, then please raise your hand. I'm not sure, usually I do Teams, so I'm not sure whether you can raise your hand in Zoom, but I assume so. Why and how? So
you can, Kees. I don't know how to do it either. I've not used it for a long time, but okay. If you know how to do it, feel free to go ahead. Sorry.
Yeah, and Anastasia, yeah, you're sort of moderating, so because I may not see all questions or all hands raised.
If I can, I'll address them.
Yeah. So gas well performance, yeah, it's not a constant. Most reservoirs, gas reservoirs deplete, and as reservoir pressure depletes, your gas well production and pressures will change. Will change eventually quite dramatically. But besides the drop in reservoir pressure, also your productivity could diminish or change, as well as your outflow performance. And in general, you want to keep an eye on how your well is doing through time, and you want to keep that tracking as simple and automated as possible. And for gas wells, we're in the fortunate condition that a lot of the parameters, relevant parameters like wet gas rate, wellhead pressure, flow line pressure, wellhead temperature, choke size, they're all nowadays are all recorded continuously, real time, high frequency. So yeah, a lot of data is available to make sense of. Bottom hole pressure is not always recorded. Not all wells, or well, I guess I'm not sure what percentage of wells are equipped with downhole pressure gauges. But for gas wells, you can actually make a fairly good estimate of bottom hole pressure just based on surface data. And we'll show how you can plot that real-time data relative to the well performance relationships, and then you can sort of equip the whole thing with alarms if things happen that you don't like. And you could call that an operating envelope. Yeah, we'll sort of show how that looks like. And obviously, what you want to do in the end, you want to get a bit of an insight in how your well performance parameters change over time, and that will be very, circumstance specific, location specific, reservoir specific. And we'll show an example of how condensate dropout may impact inflow performance, and we'll look at how generic surveillance to be able to estimate connected volumes and reserves, how that sort of works. Now let's go to the bit of fundamentals. So gas well inflow performance. So inflow performance describes the relationship between the pressure drop between the reservoir and the flowing bottom hole pressure and the production rate. So what I basically found, I've worked with quite a lot of inflow relationships, and the one that's I find easiest to use is the Forchheimer equation with only the Darcy inflow resistance, and you see how that looks like. And it's a p-squared formulation rather than pseudo pressure. And having just a single inflow resistance term, inflow performance parameter, may sound a little bit simplistic, but it's actually it's pretty convenient. And if we address this inflow resistance specifically, the Darcy one, it's basically dictated by a number of parameters, and you see the equation down here. It's dictated by viscosity, drainage radius, skin, completion skin, and the most dominant parameter is your permeability height product. Yeah, so the overriding parameter that drives inflow performance is the KH, as we call it, of the reservoir. And in the plots on the right, you see KH on the horizontal axis, and then you see the inflow resistance on the vertical axis. And you can see that you can change viscosity, you can change drainage radius, you can change skin, but overall the main parameter is KH. And here we've sort of introduced a range of domains. So we can call about prolific wells would have an A of less than 1 in these specific units, bar squared 1,000 standard cubic meters a day. Between 1 and 10 are good wells, 10 to 100 are moderate, 100 to 1,000 are poor, and more than 1,000 we call them tight. Yeah, so that's sort of a classification that you can do if you have those A parameters. I'm not showing it in this presentation, but the A is also quite handy because if you have an idea of the order of magnitude of some of these parameters, you can also estimate your KH, which could be quite useful. And you could say, well, okay, but I do a pressure buildup and I do a pressure transient analysis, and I get my KH, and I also get my skin. So it's a lot better. Yeah, in principle, that is a lot better. However, in a multi-layer reservoir, your PTA usually gives you the sum of KH for all your multiple reservoirs and an average KIN for all your zones completed. And actually, if you measure the inflow performance per reservoir layer based on a multi-rate production logging suite run, then you can actually get A per zone, and you can get also KH per zone. That's just a bit of advertising for both for multi-rate PLTs and for using IPRs, inflow performance relationships, and the resistance term to estimate your KH. So it's not a bad wet finger estimate that you get. Okay, that's inflow. So we keep it simple, just one inflow performance parameter. Outflow is similar. I think a lot of you may be used to the VLPs, vertical lift performance data that Prosper, for instance, generates. And you see in the figure on the right, you see the red circles. That's like Prosper output, a VLP at a certain tubing head pressure of 35 bar. And what we're aware of is that this VLP typically shows a minimum, and the minimum is actually where the flow regime changes. Yeah, so for higher rates, higher gas rates, fluid and gas, they are sort of in an annular flow regime, which has limited hydrostatic, and which is actually the regime you want to be in because it's most efficient. But then as your gas rate drops, your flow regime drops, changes to churn, slug, bubble, and that's when you create more back pressure in your wellbore. And what we also know is that as soon as you go into this, what we call gravity-dominated part of the VLP, then trouble can start. Yeah? So instability, well instability, intermittent production typically starts to the left of the minimum. So that's why we always like to characterize this minimum. And this minimum, people also refer to it as liquid loading, and the rate that it happens at as a liquid loading rate. And you can describe that by that liquid loading rate by a what we call like the Turner equation with a Turner constant. Yeah, and that this is sort of a well-known expression to describe that point where instability can occur. More important, you also want to describe obviously the stable outflow relationship. That's described by the right-hand side, and that's easiest described by this expression that you see here. People sometimes refer to it as Coulomb-Smith, and what it basically consists of, or is driven by, is two parameters. One is hydrostatic, that's the B, and the other one is friction, and that's the C. Yeah, so, and there's a few quite elegant and simple expressions by which you can calculate B and C. And basically B is determined by your gas gravity and by your true vertical depth. And then the friction is determined by your long hole lengths. And the main factor driving your outflow outflow friction is ID. Yeah, if you have twice as small tubing, then your frictional term goes up 2 to the power 5, which is like, I think, a factor 16 or 32, either one. Okay, so that's a very simple expression for outflow. There's a specific expression for a shut-in well. If you have a shut-in well, you're not transporting liquid to surface. The liquid drains away, and you get a very elegant relationship that translates your closing tubing head pressure into your closing bottom hole pressure by a simple constant. And this one works actually very well. Okay, now obviously B and C, these are sort of approximations. Reality is always a little bit different. And also this minimum rate expression is also a simplification. And especially if you have wells that produce a lot of liquids, so if your WGR really goes up a lot, that's the small figure that you see here. Is basically, you see this minimum rate, the liquid loading rate plotted against WGR. And you see here at lower WGRs up to 10 barrels per million, or 60 cubes per million cubes. The liquid lowering is quite constant, but then actually it gradually decreases until it becomes almost zero. Obviously, if WGR goes over 1,000, you're more talking about a water well than a gas well. Yeah, but it is there is something to consider. Okay, so we did inflow, we did outflow, but we don't have bottom hole pressure. So actually, what we usually see is surface well performance. Yeah, the relationship between tubing head pressure and flow rate, and we refer to that as the PQ relationship. And the benefit of having those simple inflow outflow relationships is that you can design, or you can calculate, you can derive that the well performance, the surface well performance relationship becomes an analytical expression. And you can either write it as tubing head pressure as function of gas rate, or you can invert the whole thing, and then basically you can write gas rate as function of tubing head pressure. And then the other parameters that are appearing in that relationship are all the usual suspects. Is the inflow parameters, reservoir pressure and inflow resistance, and is the outflow parameters, hydrostatic and friction. And if you have those parameters, then you can actually make a plot like this, where the bright red shows you the PQ curve, relating tubing head pressure and gas rate. And in the same plot, you can also plot the inflow performance relationship between bottom hole pressure and flow rate. And then obviously the difference is the pressure drop across the tubing, yeah, consisting of hydrostatic and friction. Yeah, so that's quite convenient. So you can get an analytical PQ expression, and what will then happen, and we'll use those expressions to make this operating envelope. Yeah, and what I'm saying here, okay, depletion causes steady reduction of reservoir pressure, indeed. So as your reservoir pressure drops, obviously your IPR will drop, and your PQ curve will drop, and you get like a range of curves, sort of shrinking down to the origin. And okay, let's go to the next one. And you can then use the same expressions to construct this operating envelope that you see in this figure. So you have the IPR on top, and there's a few data points just as example. And you have the PQ curve at the bottom in bright red with the same data points. And then there's a range of other stuff in there. And that basically defines your operating envelope. So there's the drawdown max. So if you define a certain maximum drawdown, say 5 bar, 10 bar, 100 psi, 200 psi, you can actually calculate where that maximum drawdown is reached on those curves. Yeah, so in this case, for 5 bar, for these specific parameters, inflow, outflow, this would, yeah, you would be able to go to up to 200,000 cubes a day, and then you would reach your maximum drawdown. So that's one element. The other elements which are in the curve are the purple one. That's your minimum rate. That's your liquid loading rate or Turner rate. That's the rate below which you could get instability and intermittent production. So that's actually the purple one. And then you have the green one is your erosional limit. So if you specify a certain maximum gas velocity above which you expect erosion to happen, then you can actually draw this line as an erosional limit warning. And then the other thing that sits in here is the flow line and choke pressure drop, or basically the choke performance curve. So if you have a certain flow line pressure and you have a certain choke size, you can calculate what you expect in terms of tubing head pressure. And obviously, if your actual tubing head pressure is a lot higher than what your choke performance curve will predict, there will be something wrong with the choke. Yeah, it will be blocked. There could be scaling. Obviously, if the pressure is a lot lower than what you calculate using your choke performance curve, then probably the choke is eroded. So that there's quite a few things that you can read off using this operating envelope, and it's all based on quite simple expressions that are quite easy to program, either in Excel or if you want to do an online web-based tool, you can use the same expressions. So this web-based tool this is a web-based tool made by one of the operators that I worked for. And it's just a screenshot, and what you see is all the usual stuff. So you see in purple you see the PQ curve. In red, actually, there's a PQ curve which is calculated at the reservoir pressure, which is 95% of the original reservoir pressure. So, and then you see the liquid loading line, the erosional line, and there's also this drawdown limit. So then you can equip this operating envelope with alarms. So you could say, okay, as soon as I go below the purple liquid loading envelope, I would flag a liquid loading risk. If I drop below this 95% reservoir pressure line, I would flag impairment or depletion. And it would be time either to look at inflow improvement or to adjust your well parameters, your reservoir pressure. And then obviously if you go above a certain rate, above the erosional line, you could flag erosional risk. Yeah, so it's quite straightforward to equip the plot with alarms. And what you do now is that at any moment in time, you can define an interval of time that you want to collect your real-time data from, consisting of tubing head pressure and flow rate, and then you just plot all those points within that operating envelope. Yeah, so then you can interrogate your well performance over specific intervals in time, and you can see whether they're changing, how they're changing, and whether they get you into trouble, or whether maybe you only just have to adjust your reservoir pressure to keep up with depletion. Now let me show you a few examples using this sort of the same web-based tool. On the left-hand side, the left-hand picture is your PQ plot. So purple again is PQ, and the red is your warning 95% of reservoir pressure. And you see the liquid loading line and the erosional line. And here the center plot is actually the calculated bottom pressure data plotted against the IPR that we assume. On the right-hand side, you actually see time-based. It's like the time interval, the real-time data plotted across that time interval that you're looking at. So in this case, you see how points are hovering. They're quite high. We're operating this well at a very small choke. It's still a new well. So you see flowing tubing head pressures are above 300 bar. And another aspect is that at those pressures, with that large pressure drop across the choke, liquid loading doesn't really happen where you expect it to be. Like a turn of velocity, you can actually operate quite easily far left of the liquid loading rate without seeing any instability. Yeah, you see that clearly illustrated here. On the right-hand side, you see a well going through an intermittent cycle. It's maybe difficult to see, but in the time-based plot here, this part, the blue one is actually rate, wet gas rate, and the brown one is tubing head pressure. And what happens if you dump all those points in that operating envelope on the right, you'll see the well sort of starts here. This is where it should operate, but then you see how actually the points are drifting at constant tubing head pressure. Points are first drifting towards the liquid loading line, and then they're shooting left even further. And what's actually happening here is that this is a well that had halide scaling, sodium chloride precipitation downhole. So here actually first halide starts blocking outflow or inflow, and then once you reach liquid loading, the rate further collapses. And then actually after a certain amount of time, the well gets rid of the liquid, also gets rid of the halide, and returns to the original performance. So you have this sort of intermittent cycle, which is not only due to liquid loading, but also due to halide blockage. Okay, so yeah, so that's just illustrating how you can build that operating envelope quite simple means. And if you have real-time data, you can really, every time interval, you can see how your well is doing. Now, long term, if you collect all the data over a longer time period, you can sort of start to see how some of those parameters behave in time. Now, one of the well-known phenomenon in gas condensate reservoirs is condensate dropout, which happens because you're entering you go below dew point, and a lot of the condensate will drop out, and then the impact is that the condensate saturation in the reservoir increases. Still, condensate saturation is not high enough to allow condensate to flow to the wellbore, but the condensate saturation does diminish the gas relative permeability. So conventionally, people say, okay, as soon as you pass dew point, your inflow resistance, your inflow performance will go down, your inflow resistance will go up, and that can be significant. Now, these are two examples. They're both actually gas condensate fields that are in tightish rock, and they were both hydraulically fractured by multiple hydraulic fractures. And on the left-hand side, you actually see data that's based on multi-rate production logging. So that's actual production bottom hole pressure data. So these A factors, and it's not the inflow resistance sec, it's actually a pseudo pressure inflow resistance, because we're dividing by viscosity to make it independent of reservoir pressure. So if nothing would happen, then all these wells with all their inflow resistance terms should be flat. So there should be no variation as reservoir pressure declines from around 520 to around 50 to 100 bar. So what you do see actually in these wells is that indeed, so as you pass dew point, which sits around 450 or to 500 bar, inflow resistance does go up, maybe by a factor 2. But then actually, after you've reached like 100 to 150 bar and you deplete further because you have like second stage compression, you will actually see that the inflow starts improving again. So it's like the condensate dropout, which caused the impairment initially, then at lower tubing head pressures, which causes lower bottom hole pressures, either the condensate re-evaporates and or is being stripped out because of higher gas velocities. So it's sort of a self-restoring effect that, this condensate impairment disappears as you reach low enough tubing head pressures. On the right, you see a plot of similar data, but from another operator. And here we actually only had tubing head pressure data. So here we had to derive inflow performance using that operating envelope that you saw. But you do see the same trend. So at higher pressures, inflow, which first actually comes down, inflow resistance comes down because of cleanup. But then as you go below dew point, pressure inflow resistance goes up, but then as you go low enough, it actually improves again. So that's quite an interesting finding, because usually people assume that condensate dropout is there to stay forever, but it's quite evident that it is not. Okay, that's one example. The other more mundane application is where you use the reservoir pressures that you find from matching your well performance at regular intervals by using that reservoir pressure data in a material balance sense. So what you see here is a material balance plot where you have pressure data both in blue from the IPRs, inflow performance relationships, and you also see some pressures which are based on closing tubing head pressures, as you shut in the well, in green. And you can clearly see that if you plot that, that material balance parameter, reservoir pressure over gas deviation factor versus cumulative produced volume, you sort of can distinguish a quite clear linear trend, which would then dictate or would tell you how much gas volume you have connected to that specific well, which in this case would be around 450 to 500 million cubes, standard cubes. You also have another source, obviously, of which gives you a similar number. That's the what you can refer to as rate cum, or the Klein curve analysis. So here we're actually plotting the gas rate, the monthly average gas rate, versus cumulative gas production. And here you see the well history, but then you see the limitation of this rate cum business is that you only get a reliable rate cum slope and linear trend as soon as you've reached a constant tubing head pressure. So in this case, actually, the well was kept producing at very low rates initially, at high tubing head pressures, and here it was ramped up, but here it was still choked, and only for the last part we hit constant tubing head pressure, and that's when you get a clear linear trend, and then it dictates a connected volume which is comparable to what we had from material balance. And then once you have those two trends, you could either use material balance and a minimum reservoir pressure. That's expressed by this analytical expression again, which follows from the IPR and VLP expressions. And you can derive an ultimate recovery that way, or you can use the rate cum and an estimate of your minimum rate that you can achieve, and that way you can get another estimate. And in quite a lot of cases, they're quite close. Now, obviously, these should be considered like 1P, proven numbers, because as your rate declines, there's scope for slow gas coming in, and for actually these curves actually starting to deviate, becoming flatter, and you're connecting more gas that you only can see when you're wait long enough in time. So this is so the blue points are all from the well performance curves. You see the green point here is quite a bit lower. So why does it happen? That happens because if you just close in your well on choke, most chokes are leaking, maybe not initially, but certainly after a number of years. So then your closing tubing pressure that you see is not actually the real closing tubing pressure. It's still impacted by leakage. So that's the reason that closing tubing pressure sometimes become unreliable, unless you have a hard shut-in on a valve. Okay, let me see what I can move. Okay, we've already reached last slide with conclusions, recommendations. Yeah, so I really advocate using the simplest analytical expressions possible with the least amount of parameters, because in reality, usually our data accuracy or availability or reliability is not big enough that it justifies making things more complicated. I know much more complicated models exist, but usually you don't have the surveillance data to meaningfully match them. So why make things complicated? It's good to be aware of all the things that you're actually not capturing, but capturing them is not always realistic. Okay, and in gas wells you have all that real-time data. So you can use that very actively and very meaningfully to match your well performance curves against. And you can use the same relationships in operating envelope that you can equip with alarms against the most common mishaps. And then there's just stating what we find from the two examples, that indeed at low enough reservoir pressure, at least in these two hydraulically fractured formations, where we know condensate dropout doesn't, provides less impact than in a situation without fracks, but in that situation it seems to disappear. And if you're doing any volumetrics or any ultimate recovery estimates, I would always advise start with a simple, one tank material balance exponential decline. At least it gives you 1P reserves that should be pretty solid. Now all these tools easy to program in Excel. but they can also easily be migrated into web environments, because a web environment is superior in terms of sharing data and keeping keeping a single set of parameters in your whole organization. Okay, that was it. So over to any questions that you may have, any suggestions, anything you like to share.
Okay, thanks, Keith. I think because of the number of participants, we can take the questions by voice. I'll unmute everyone if I can work that out. Yeah, just if you've got any questions, just shout out, or
Is it any possibility to share a copy of this presentation by email?
Yeah, we're recording the
PDF.
of the the slides. That's up to Keith. We don't
yeah,
normally.
you can.
Yeah, if you're happy to do that. Yeah.
No, we can. I mean, I've shared it with the SP
okay.
as well, so I don't
That's
see
fine.
a reason not to share with the audience. Yeah.
Sure. Okay. Yep.
Great.
Yeah.
Thank you.
Okay, and we'll send you an email when the recording is available as well on YouTube.
Yeah.
Okay. Any other questions?
All clear as mud.
Yeah. No, no, it was quite clear, and as you said, keeping it simple, which is good. Okay. If there are no questions, Keith, thank you very much for the presentation and taking the time to prepare it and deliver it today. And thank you for joining the webinar, everybody.